Okay, so at the end of the last video, I think I said that we were going to talk about implicit differentiation, but what I meant to say was logarithmic differentiation. So what happens here, we are going to use the implicit differentiation that we learned in the last section, and also these log laws that we just went over, which will help us simplify the problem before we use implicit differentiation. So, the steps, first off, maybe I'll switch back. So the first step is to take the logarithm of both sides. Right? And then next, you use log laws to simplify. So, yeah, we'll go over. I'll just write down all the steps and then we'll talk about them. Next, you differentiate implicitly. And so, right, okay, we differentiate implicitly, and then you just need to get dy dx by itself. So really, these last steps are, I would say they're sub-steps of the third step. So I'll write them this way. So when you differentiate implicitly, you'll always have natural log of y on one side, right? And the derivative you'll get 1 over y times y prime equals some other stuff. Okay, and so that will hopefully help make this part make sense. So the next step would be to multiply by y to get y prime alone, right? And then you just substitute the formula for y to get your answer all in terms of x. Okay, now hopefully this next example will make some of this a little bit more clear. Okay, so we're just going to follow the steps. The first thing is to take the logarithm of both sides. We usually use natural log just because the derivative is always really nice. So we'll take the natural log of both sides and see that this is something that we could differentiate using quotient rule, chain rule, product rule. We would have to use all of them, and it would be really nasty. So this actually is going to make our computations a lot nicer for problems like these that look all funky like this. Okay, so we would take the natural log of the other side. I'm actually going to give myself a little bit more room. So of this entire thing, 2 minus 5x, square root of 2x squared minus 1, that's the denominator, and then just x to the fourth in the numerator, right? And so if I wanted to use my log laws to make this simpler, I would turn this division into subtraction. That's one of our log laws. So I'm going to write this over here because I know I need the room. And so first we would get natural log of x to the fourth minus the natural log of this stuff in the denominator. Oh, 2x minus 5, or 2 minus 5x. Okay. And then to simplify even further, I could split this into a product, right? Because this is the product of two functions, I can turn that into addition. So I'll put parentheses here. I would keep on wanting to do that. 2 minus 5x plus natural log of 2x squared plus or minus 1. Okay, and then I would do one more simplification before we start to differentiate. So we haven't even gotten to the differentiation part yet, right? We're still just simplifying using log laws. And okay, I might want to distribute that negative. So natural log of x to the fourth minus natural log of 2 minus 5x minus, notice that this, I can rewrite this as 2x squared minus 1 to the 1/2, right? And that 1/2 is being applied to everything inside of the natural log, so I can use that log law that lets me pull the exponent out front. Technically, I can do that to this one too. So maybe let's just go ahead and use that exponent law on this function, and then, or on this logarithm, that chunk, and then also on the end. So we get natural log of 2x squared minus 1. Okay. Now, remember that dealing with addition and subtraction when we differentiate is actually pretty easy. Those were the differentiation rules that were easy to remember. The derivative of the sum is just the sum of the derivatives, and so on. So when we use the log laws to simplify, to turn all of that multiplication and division into addition and subtraction, we simplify the computations that we have to do to find the derivative, right? So that's the idea behind logarithmic differentiation. Now, what I want to do is now differentiate. I do have to use implicit differentiation because I don't have, because I have a function of y on this side, right? So this is an expression that involves x and y. I can differentiate implicitly. So I like to draw an arrow and write differentiate just to be clear that I've now started to differentiate, right? Okay, so just to do this in more than one step, I'll write, so we're differentiating, that means take the derivative of both sides. We've now started our implicit differentiation, so we're now in step 3, right? Okay, so this is what we want to do. Everything on the left-hand side is just a function of x. So we really just treat that normally. We take the derivative normally. And so we'll just go through and do that, and we'll deal with the left-hand side in a second. So the derivative of natural log of x, we just learned it's 1 over x. So we get 4 times 1 over x for that one. Here, this is... we would get 1 over 2 minus 5x times the derivative of the inside, which is just 5. And then lastly, we get 1 over 2x squared minus 1 times the derivative of the inside, which is 4x. Right. Okay, and then now dealing with the left-hand side, what you will get in every single one of these problems is the derivative of the natural log of y, okay? And so this side will always be the same. Maybe I'll put, actually, let's do the derivative first. So first we have natural log of y, that gives us 1 over y, right? And then we multiply by y prime, because y is a function of x. So this piece will always be the same in every problem. Okay, and that is what I was referring to up here when I said, oh, that doesn't make sense. So I meant to say on one side, usually the left-hand side, because we usually write y equals whatever we're trying to take the derivative of. on one side we'll get 1 over y times y prime. So see that when we took the derivative of this, we got 1 over y times y prime, and that's what you'll always get. And so finding y prime is just as simple as multiplying by y to get it by itself. So it'll be y times this stuff and then I can cancel 2 out of there, so I just get 2x over 2x squared minus 1. And then in the last step, we replace y with the formula that we had at the beginning for y. So this one right here, right? So this is the step where we replace y to get, so we have a formula for y prime that is entirely in terms of x. Okay, so we replace y with the formula from the beginning. Okay, and so I'll go ahead and do that. So that means that y prime is equal to, copy down this 2x squared minus 1, x to the 4th. So that's y, and that will be multiplied by this other stuff that we got, that we computed. I'm going to hide that. So 4 over x minus 5 over 2 minus 5x minus 2 over 2x squared minus 1. Like that. And that is our answer. I'm going to do in this color right here. And even though it seemed like a lot of work, it's actually still significantly less work than it would be to do this problem using your regular rules, because it would just get so drawn out and terrible to simplify. And it turns out this is the nicer way to do this. Okay, and then so I'll just finish up by talking about a particular type of function that we can now differentiate now that we know how to do logarithmic differentiation, and that is functions of the form where you have one function taken to the power of another function. And so one example of this was that x to the x function that we looked at in class last time. And this is going to, we know that we can't use the power rule on this, and we can't use the exponential function rule because in each of those cases we don't have a constant and a variable. We have two variables, so they're both changing at the same time, and neither of those rules apply. So what we can do now, we can do this using logarithmic differentiation, and how we do that is we take the natural log of both sides. So we always start these problems that way. And then we can use that exponent rule to take this x out front. Right? So we can rewrite this as x times natural log of x. Okay. And then what we have is on the right hand side we have a product. So if we want to differentiate, remember on the left hand side we always get the same thing, but we can go through it. So we get derivative of natural log of y is 1 over y times y prime. And then on the left hand side we use the product rule. So that would be 1 times natural log of x plus x times 1 over x, right? So this actually simplifies quite a bit because we just get natural log of x plus 1, right? Now to find y prime, we just multiply both sides by y, to get y prime by itself, and so plus 1. And then the last step is to replace that y with our formula x to the x. Okay, and then we'll just do one more example. So this is not the only type of function. It's really any time we have a function taken to the power of another function. So see that here we have sine of 2x, and then we also have the variable x in the exponent. So you should look out for this. There's a strong temptation to try to use like the power rule when you approach a problem like this, but you really do need to use logarithmic differentiation. Okay, so I'm going to rewrite this as y sine of 2x to the 3x, and then take the logarithm of both sides. And then our work will go very similarly to the previous problem. So that 3x in the exponent, we can bring it out front using our log law regarding exponents. Right? And then we don't need to do any more simplification. This is fine. Now we just differentiate. And remember, we always get 1 over y times y prime on the left-hand side. On the right-hand side, again, we have a product of two functions, so we should use the product rule. So we would get 3 times the natural log of sine of 2x and plus 3x. And then here we have, well, a couple layers of functions, so we have to use the chain rule twice. So first we would take the derivative of natural log, that would be 1 over everything inside of it, so sine of 2x. Then we take the derivative of sine, and that is cosine, and we leave the inside alone, so cosine of 2x. And then finally, we take the derivative of the inside of that, which is just 2. Okay? So here we have, we've differentiated everything, and then the last step is just to multiply by y, well, last couple steps. So first we multiply by y, and then we can replace that y with our formula for y. Okay, now I'm going to combine these, so 6x cosine of 2x over sine of 2x. Right, and then y was equal to sine of 2x to the 3x, and then we just copy this other part. Okay, and that is our answer. That is y prime. Okay, and so don't forget to do the comprehension check question.